Welcome to our video on differential equations transformations. Today, we'll learn how to take complex-looking differential equations and transform them into simpler forms that we already know how to solve. We'll cover two important types of first-order differential equations. First, Bernoulli equations, and second, equations with linear coefficients. For each type, I'll show you a step-by-step recipe for transforming the equation into a familiar form that you can solve using techniques you already know. Let's start with Bernoulli equations. A Bernoulli equation has the form dy dx plus p of x times y equals q of x times y to the power n, where n is not equal to 0 or 1. Our goal is to transform this equation into a linear differential equation that we know how to solve. Let's go through this step by step. Step 1. Divide both sides of the equation by y to the power n. This gives us y to the power negative n times dy dx plus p of x times y to the power 1 minus n equals q of x. Step 2. We introduce a substitution to simplify this equation. Let's define a new variable v equals y to the power 1 minus n. When we differentiate v with respect to x, we get dv dx equals 1 minus n times y to the power negative n times dy dx. We can rearrange this to get y to the power negative n times dy dx equals 1 over 1 minus n times dv dx. Step 3. Substitute this expression back into our divided equation. We get 1 over 1 minus n times dv dx plus p of x times v equals q of x. Next, multiply both sides by 1 minus n to get dv dx plus 1 minus n times p of x times v equals 1 minus n times q of x. And look at that. This is now a linear differential equation. In terms of v, it has the standard form, dv dx plus coefficient times v equals function of x. Step 4. Now we can solve this linear equation using the integrating factor method. The integrating factor is mu equals e to the power of the integral of 1 minus n times p of x dx. Using the product rule, we write d dx of mu times v equals mu times 1 minus n times q of x. Then integrate both sides to find mu v, and solve for v of x. Step 5. Finally, recover the original variable y by using the substitution formula. Y equals v to the power 1 over 1 minus n. And that's the complete process for solving a Bernoulli equation. Let's see a quick example. Consider the Bernoulli equation. dy dx plus 2, y equals x times y cubed. Comparing with our standard form, we identify n equals 3, p equals 2, and q equals x. We apply our substitution. V equals y to the power 1 minus 3, which is y to the power negative 2. This transforms our equation into the linear form, dv dx minus 4v equals negative 2x. Now we can solve this linear equation using the integrating factor method, and then recover y equals v to the power negative 1/2. Now, let's move on to the second type of equation, differential equations with linear coefficients. These have the form a1x plus b1y plus c1 dx plus a2x plus b2y plus c2 dy equals 0, where the determinant a1b2 minus a2b1 is not equal to 0. Geometrically, this means that the two lines a1x plus b1y plus c1 equals 0 and a2x plus b2y plus c2 equals 0 intersect at exactly one point. The key idea is to translate our coordinate system so that this intersection point becomes the new origin. This will transform our equation into a homogeneous form. Step 1. First, we need to find the intersection point of the two lines. We solve the system of equations. a1h plus b1k plus c1 equals 0. a2h plus b2k plus c2 equals 0. Since the determinant is non-zero, this system has a unique solution which we'll call hk. Let's visualize this. Here we have our two lines intersecting at point hk. Our goal is to shift our coordinate system so that this point becomes the new origin. Step 2. We introduce new variables by translating the coordinate system. Let u equals x minus h, and v equals y minus k. This means that the point hk in the original xy system is now the origin 0, 0 in the new uv system. The inverse substitution is x equals u plus h, and y equals v plus k. And the differentials remain unchanged, dx equals do, and dy equals dv. Step 3. Now we substitute these expressions into our original differential equation. When we substitute x equals u plus h and y equals v plus k into the coefficients, something interesting happens. For the first coefficient, we get a1x plus b1y plus c1 equals a1u plus h plus b1 v plus k plus c1. This simplifies to a1u plus b1v plus a1h plus b1k plus c1. But remember, h and k were chosen specifically to satisfy a 1h plus b1k plus c1 equals 0. So this term vanishes, leaving us with just a1u plus b1v. Similarly, the second coefficient, a2x plus b2y plus c2, becomes just a2u plus b2v. After substitution, our differential equation becomes a1u plus b1v do plus a2u plus b2v dv equals 0. Notice that this is now a homogeneous equation, where every term has the same degree, 1, in u and v. Step 4. Now that we have a homogeneous equation, we can solve it using a standard substitution. We can separate it as dv over du equals negative a1u plus b1v over a2u plus b2v. The right side is a function of the ratio v over u only. So we make one more substitution, w equals v over u. If w equals v over u, then v equals u times w. Differentiating v with respect to u, we get dv over du equals w plus u times dw over du. Substituting this into our separated equation gives us a separable ODE in w and u. From here, we can 1. Solve for w as a function of u2. Substitute back v equals w times u3. Finally convert back to x, and y using x equals u plus h, and y equals v plus k. And that completes the process for solving differential equations with linear coefficients. Let's summarize what we've learned today. 4 Bernoulli equations of the form dy dx plus p of x times y equals q of x times y to the power, and we use the substitution v equals y to the power 1 minus n to transform it into a linear equation. 4 differential equations with linear coefficients, a 1x plus b1y plus c1 dx plus a 2x plus b2y plus c2 dy equals 0. We translate to the intersection point of the two lines, resulting in a homogeneous equation that can be solved using the substitution w equals v over u. These transformations are powerful tools that allow us to convert complex-looking differential equations into familiar forms that we already know how to solve. Practice these techniques, and you'll be able to tackle a wide range of first-order differential equations with confidence. Thank you for watching.